we don't usually have like a sort of adversarial question period after the talk, so we will ask questions during, and the members of the audience should feel free to ask questions as well. And I'll take it away, Bowen.
Okay, so let me put a title up. So my main point today to talk about is a geometric perspective, basically, on some arithmetic statistic questions over function field. Okay, so the title is a bit long, it's a bit involved, but I'll hopefully give you a sense of what kind of we're trying to do, and what kind of are the recent developments and so on. So for example, it's been an exciting time. So for example, just in March, two things came up which are very related and in the same spirit as what I'm doing, but they're more like from a topological perspective, and I'll get to that. So let me start for motivating kind of what we're doing with these questions over function fields. So first is what I like to call is analytic number theory over Z. So the basic question is, you start answering the first easy questions is when you prove there are infinitely many primes, and then you start to ask yourself, well, how many primes are there in the sense that, let's say, so the idea is, there are infinitely many primes, but we want more refined question than this, okay? So, for example, we want to know, basically, if you make a box, how many primes, for example, from 1 to x. So we want to make some parameter, and we want to make some quantitative estimate of this in terms of this, parameter. Okay, we say x is going to be our parameter, and we want to say as we vary x to infinity is what are we getting? Okay, so as x goes to infinity, what's the asymptotic behavior of this quantity? Okay, and then you basically realize that this is very intimately connected. In most of these questions, so I want basically how many primes are there. I can make even shorter intervals, so I can say, okay, x to x plus h. And I can ask these questions, but basically, for most of these questions, we can cook up something very analytic. So basically, there is a function which encodes kind of your behavior, and if you understand well that analytic function, then you understand what it is. So let me define this one. So this is the Riemann zeta, basically it's the sum of 1 over n to the s, from n equals 1 to infinity. Okay? And basically most of our questions about primes are intimately related to how this function behaves. So we know this is analytic for the real part bigger than 1. Then you have a meromorphic continuation and a simple pole, so the A is to the whole plane, and simple pole at s equals to 1. And basically this translates here, if you know the Tauberian theorem, or basically Polya's theorem, so basically you know the Tauberian theorem, then you can translate the answer from this part here that I say that you have a simple pole here at s equals to 1, to basically getting the asymptotic for this. This is like x over log x. And generally speaking, if you make a lot of analytic functions like this, you cook up, basically we call them a general class of these is called L functions. If you understand their behavior, basically what the poles are and so on, there's a general theorem, I won't write it down, but basically it's the Tauberian theorem which tells us how to sum things up, basically. It will give us exactly terms that look like this, if I understand well the behavior of the poles. Okay, but now obviously you can play this game and get good results, but actually there's more to this story basically. You can't get more precise estimates because there's a barrier to this. So basically the barrier to this is that we don't know, basically there's the grand Riemann hypothesis that all these are the non-trivial zeros after Riemann. Okay, So this is the Riemann hypothesis. And we can generalize it. But the point is, what I'm trying to get at is like, if you want something more precise than this, it's very hard to get at it, basically. So, and that's where, you know, all these questions, there are a bunch of questions, for example, twin primes over Z, and so on. These are notoriously hard problems if we talk about them over Z. And in the past, like, let's say 50 years, let's say 100 years, just to be safe, there's been the idea is that there is this side of things where you can take any problem you want and cook up something analogous to that problem over function field. So basically, the second part is you can take your favorite problem over Z,
Yeah, I'd say 75 years, I think I'd say.
okay, Jordan is better than me on the history, okay? So you can, but actually the idea is I read a bit about Artin. So Artin kind of conjectured what I'm talking about, the well conjecture for curves in 1924. So kind of he wrote down those. So that's kind of like why I say 100 years just to be on the safe side. Okay, so you can take your favorite problem over Z and move it to the so-called function field setting Fq of t. So here this is the finite field with q elements, and this is the polynomial. Okay, and this idea is very, very important, you know. So what we can do is basically hope that the question we end up here is somehow easier than in that situation. The idea is there's more flexibility here. So let me say a bit of history, what happened and why do we hope things are more, you know, attackable in this situation. Well, the major breakthrough was basically the introduction, basically the proof of Riemann hypothesis, basically over function fields. So this was the major breakthrough that basically stimulated everything to be more believable, that things would work easier. So this is basically due, basically in order, kind of in, if I want to do it in a correct order. So let's see. So the work proved something like here, I didn't say it, but there's a functional equation and there's more properties, but basically the work was the first one. Grothendieck introduced basically introduced a tau homology to prove the rationality. So here there's an extra thing. You get rationality of the zeta function. So here you get. So for any variety, you can cook up. So basically, cook up a generating function out of the points of the variety over Fq to n. And what the magic thing is, in this situation, you end up with the rationality statement. Again, that goes back to 65 to Grothendieck. And the last thing is actually this part here, with I said Riemann zeta hypothesis, which is, Riemann hypothesis, which is this part, 1/2 zeros. This was proved by Deligne in 70s. Okay, so that's the major breakthrough. And this allowed us, you know, to basically get stronger results than this here. So for example, let me just give you an easy example. I told you how many primes are here, so I told you that they're roughly, so this we use for the prime counting function, we use this notation, and we say that asymptotically speaking, there are roughly x over log x primes. Now let me show you how you translate that statement there. So the idea is, what we're going to focus is, basically we have monic polynomials of degree n. So let me start filling in some, basically, these are entries in now a very rich dictionary between Z and function fields. So we call this set Mn, okay? And obviously, we're in FQT, so they're exactly Q to the n of these polynomials. And this will roughly correspond to x, okay? So that's going to be the size of our box. This is where we're looking at. Okay, what's the term log of x? So, log of x, if you just use your calculus knowledge, and all students are really bad at that, okay, this is going to be n log q, okay, and we ignore this part. So basically, this will just amount to n, okay, because log q is just a constant, so we're just going to throw it away. Okay, so that's what we get. So basically, we expect, if you just use the dictionary and things, cross your fingers that things work out the same, you expect q to the n over n. Okay, so expect this number of irreducible polynomials. but actually can get a precise count. I mean, it's an easy like 741 for your quals exam. It's an easy exercise to actually get a precise count. So you can get a precise count of these. Namely, let me just write it like this.
I don't think that's easy enough for quals. I wouldn't put that on the qual.
Okay. So this is 1 over n nu d.
He would have passed the code, so you put whatever.
No.
Okay. So you get precisely more. It's more than you expect. So basically, if you look at this, you get exactly. So if I write it now, the way it should be, this is q to the n over n plus O of q to the n over t, which we already expect there. So if the Riemann hypothesis was true there, then you would see exactly the square root of x, or the term there. Okay. So that's why I said that here things are nicer, and you can get more sharp estimates than on the other side. Okay. So that's the story. That's why we kind of want to take problems here and get results here, and it's a pipeline between these two worlds, and you can go back and forth. Okay. So that's all good and nice. Now the idea is that I want to get to geometry. So until now, I kind of told you here that secretly I use the word which is a tau homology, okay? So that has to do with the geometry of our situation, okay? So let's go to the geometry and see. So if I go to the geometry, what I'm going to use basically, and I use mostly in my PhD thesis, is basically a counting formula. So we can count points on varieties over finite fields. Okay, so roughly what actually this count here, if you want to be a geometer, what you actually do in this count here is, if I want to rephrase it in terms of geometry, I would say, okay, I have the affine n space over fq. Let's say fq, fq bar. And I want to count degree n points over this. Sorry, affine, sorry. So count degree n points on this affine line.
So you want to be exact A, not to the S equal A.
Yeah, exactly. So there is exactly degree n, basically, points on this one here. If you count degree less or equal to n, then you end up with q to the n, because you're summing over all possible things that, so the idea is if you just, if you do that, then you end up with q to the n. Okay. So this is the geometric version of this, and we can use more general things to do more complicated stuff. So let me say what I want to do. So basically, we're going to consider a variety, V over Q.
Let me ask just a question.
Yeah.
So is counting things of degree exactly n, like counting primes of size x?
So roughly, so I kind of lied, you're right, I'm kind of lying, because I'm doing basically here, I'm doing this booted version, x to 2x, okay, so everything has kind of size x basically here. So, but we're kind of always kind of ignoring this issue most of the times. We're just, pretending, it's not going to be a big difference in the end to make our predictions, go back and forth. But yeah, you're right. We should be
Well,
aware of
I
that.
think you counted polynomials, its absolute value is between q to the n and 2q to the n.
Okay, so if you do q to the n to twice, well, the idea is you have to say what this means, okay, first, which, either means you're saying, okay, the first coefficient is 1 or 2, and that's kind of, yeah, so the point is, what I want to say here is that the valuation is the degree, so, yeah. So, if we were on Z, the valuation of a number is just the absolute value, which is a real place, but here the valuation of a polynomial is its degree, okay, that's...
And the prime is irreducible.
Yeah, so basically when I say a prime, it's irreducible, basically. So the problem is when you say q to the n between q to the n and 2q to the n, it's like, kind of makes, I don't know, like,
You probably have to go to the end to go to it. Otherwise, it'll be pretty tough.
Yeah, so it makes things a bit weird. And then again, that's why kind of we always work in these kind of boxes, monic polynomials of degree n, because we want to avoid Also the idea is also Mn, just saying this, it's also actually like positive integer, so that's why we kind of use Mn. Because if we do the other ones, we can consider, so that the idea is the Mn actually corresponds to the positive integers. Okay.
Okay, so if you, let's say you wanted to count, instead of you wanted to count the monic irreducibles of degree exactly n.
Yeah.
We wanted to count the monic irreducibles of degree less than or equal to n.
Yeah, you would basically.
What does the answer look like then?
So let's see. You would have to sum up all these bunch of things. And the idea is, if you have a number n, if you sum up all these things, so the idea is, I already know that if I sum up over divisors of n, I'll get q to the n. So the idea is I'll get
What is it in the number field analogy?
Okay, so in the number field analogy is
What is it?
yeah, we're summing all the primes basically from. So basically, we're kind of want to sum up all the. So basically, want to sum up the one module function. Yeah, and so that's from 1 to x. And the idea is, in this case, let's see. The point is, we know an asymptotic for this.
Are you summing the von Mengel function, or are you summing? I think you're just summing the characteristic function of the primes.
Yeah, I'm summing the characteristic function.
Which is very similar, but it's a different sum, so it's worth that.
Yeah. So the idea is that that's what we do basically. Yeah. So yeah, the idea is you're summing up the characteristic function of the primes.
What's that usually the one or what's chi p?
Yeah. So this is the 1p. Let me just say 1p. The characteristic sum of the primes. This is the number of primes less or equal to x basically. But if you're summing all the irreducibles, basically, yeah, I don't know what you would get, because basically that one has a fraction there, so, I mean, if you want an estimate of what the size should be, or,
Yeah, the order of magnitude.
so, the order of magnitude should be q to the n, basically.
Okay, so what's the order of magnitude of primes up to x? You already said this, but I want to just make sure we're on the same page. Order of magnitude of primes up to x.
Yeah, this is x over log x.
What about between x and 2x?
So, x to 2x, if we use that one there, you get basically 2x. Basically, if I'm just using dumbly that formula, you get this, which is, it's, sorry, x over log x. So if you do the algebra, then you get roughly x log x, some constant there again.
Different constant, right?
Yeah, it's a different
So
constant.
it's
You're
the
right.
same order,
Is it
so,
Yeah, it's a log 2, which is kind of.
well, it depends on 2. I mean, it might be exactly the same for 2, but it could be different.
If you think x is big, really just the same.
I think if you divide that by x over log x, I think the limit will still be 1.
Yeah, exactly. So the point is, so I don't know. Let's just do this.
Okay.
No, then you ignore the 2. That's it. 2 didn't do anything.
Okay, so the idea is you get x1 minus log, so you get x log x minus x log 2. So basically you get the log x minus the log 2. So in the end, it doesn't. So I was breaking out this
Depending
into.
on 2. The fact that it was 2.
Right.
meant that you get
If
exactly.
x is big, well,
Yeah. Okay.
Okay, so then what do you think happens in the function field setting? So now, and we just talked about primes up to x and then between x and 2x. So in the function field setting, you have two possibilities. You could take degree n exactly irreducibles or degree up to n.
Yeah, so the idea is it will just get smaller terms into this sum. So basically, the order here of q to the n over n stays. But the idea is, the problem is, if you make n comparable to q, then you get into sort of funny business, like, if you, because then again you have, so the idea is you have for n minus 1, you get q to the n minus 1. So you get q to the n, still this one here as the main term. Yeah.
Yes.
Okay.
Good. Great. Thank you.
No problem. Okay, so let me get back to what I wanted to say about actually this part here. So I said a bit of a geometric setting here, but let me make it more clear what you can do. Because basically this will be like, the easiest example is here, A1, but I want to do more general things, and then I'll give you a concrete example, which is everybody's favorite example. So I'm trying to take a nice variety, which is, so project this smooth. Okay, and the idea is that, let's say the dimension is n. Then we have the Grothendieck Lefschetz trace formula, which basically allows us to count points on this variety. So the idea is we have the number of points on the variety. It's going to be this sum here, minus 1 to the I, times the trace of the Frobenius on hi et al. So Frobenius at q of hi et al. Of p real one coefficients. Okay, so let me unpack a bit what actually is happening. So the idea is, first, I have to tell you about the Frobenius. So the idea is, what is this guy? So Frobenius Q just does, the idea is, this is the geometric version, so I have to be careful. So what I'm going to tell you is the arithmetic Frobenius, so maybe I should go to do something else. Okay, so let's not write this guy as Frobenius on this. So there's this map, x to the q, okay, which we call, so this is, this is the arithmetic Frobenius. Okay, and the magic thing of this map is if you have x equals to x of q, then you exactly end in fq. So the idea is, if this happens here, then you are in fq. So the point is that when we're doing this guy here, secretly we're replacing this with the fixed points of this map. So this is the number of fixed points of this map. And here, we're thinking about this over the object right order. So this, map acting on V, and I change it to FQ bar. Okay, so I just act on points on this variety, and this is what I'll get basically. If I want to count the FQ points, this will be the fixed points of this map acting on the FQ bar points.
Vlad, I think there's a question.
Yeah.
Sorry, I always feel confused about the arithmetic Frobenius, geometric Frobenius.
Yeah.
So when you write x to the q, you mean x the point of this variety?
So x is a point, okay? So x is a point, or x is in f cube simply, and then you act coordinate-wise. Because that's why I said it's projective, because I have coordinates I can, So the idea is that's what's happening here. This on this side, I have to be careful. What I'm actually using is the other guy, is the inverse of this map. Okay, so the Frobenius acting on this will be the inverse map. Okay, so this is called, so this guy here is the inverse, which is the geometric Frobenius. Okay, so this is
Actually make any difference due to the trace.
So let me think a bit about it. So, yeah, it really doesn't. So the trace will be basically, yeah, it shouldn't make any. In some cases, yeah, you have to be a bit careful. Yeah. I would rather take this guy. So the idea is you have to be a bit careful about this, because the idea is why have to be careful is the idea is if you do one, you'll get weights which look q to the I, and the other one will give you q to the minus I. So you want to get the weights in the correct order. So this The geometric Frobenius basically is this, the guy which gives you the correct weights, actually. Okay. And now I haven't said, so there is, now I said what this is, but there is now the magic thing that happens in the Weyl conjectures proof and Grothendieck's construction of a tau cohomology is that what I'm writing here makes sense because you can make this geometric Frobenius act like a linear operator on this space, basically. This is constructed as, basically think about it like a vector space, and now you have a linear operator, you can take its trace, basically. And now, I won't say too much about this part. So, in most of my setting, this part here, I can just pretend this is singular cohomology over C. So the idea is, there's a general theorem which in my case will give me the action for free of the Frobenius. So the idea is, one thing I want to make is that computing with this formula is generally hard. So we can only compute stuff out with this formula. We have nice varieties, but in general it's really hard. So one example of an achievement is like Jordan's recent paper with 3-Tran and Thomas Church, where they actually use this formula. What?
Not Church, Westerland.
Well, yeah, Craig Westerland, sorry about it. So there is where they use something like this, but on a more complicated space. So this will not be as nice, but you can still use a Grothendieck space formula. The idea is, this computation doesn't work out, but at least you can bound things out. So the idea is you can obtain upper bounds using this. So the idea is, the warning is that using this to compute is generally not something you can do. You can only do it in special cases, and that's an important thing we have to remember. And what I said is like, this guy we can somehow recover what it is as dimensions. So the idea is there's a general theorem which is called the arcing comparison, which tells you what these groups are basically as Betti numbers. So basically the dimensions are recoverable because you can just, okay, if you have V defined over Z, so if you have a model for V over the integers, then you can talk about V also over C basically. And you have C points, and there over C you have singular cohomology. So basically there is a way to go here from these guys. Basically you can just recover, by forgetting the Frobenius action, you can just recover the Betti numbers from this setting. Okay, you just compute singular cohomology here, and you can recover the Betti numbers. But not the Frobenius action. So that's what I said, is this is kind of the hard part. So what, basically for most varieties, what we know are bounds. So the idea is, the major result of the second paper of Delino on Weyl 2 is that we can bound these. So these weights, these weights of the Frobenius, the powers by which it acts, are bounded by q to the I over 2 in absolute value. Okay? There's also more structure in this one. I mean, you can decompose this space into a weighted space, but I won't get into that because that's a more like tedious thing to say. Okay, but the idea is you can get at least bounds. So if you believe you can go over C and do some computations and you do this, then hopefully you can get bounds on how many points you have on your right to get some sense of what's happening. Okay, but sometimes you can actually compute out stuff. So let me give you an example where you can actually compute stuff out, and that will give you a feel of what I'm trying to actually do, and I'll give you the problem that I'm actually dealing with in the thesis. Okay, so the starting point of that, so I have that formula, and the starting point of this example is basically found in Jordan's paper with Thomas Church and Benson Farr on representation stability and so on. So, I'll give you an example. And this is, everybody has seen this example at least twice, but I'll do it again. So this is square free polynomials. Okay, so this will give you a feel of how I'm trying to compute things out. And this is, again, motivated by the same question over Z. So here, over Z, you have square free numbers. Okay? And let me give you a feel how you would count square free numbers over Z. So here, you have numbers from 1 to x. And you want to count square free numbers. So if you pretend that primes are independent, which you can just do by inclusion exclusion, if you want to be square free, you don't have to have p squared inside of you. So the idea is, if you're square free, you should have a p squared. So the local probability at the p is 1 minus 1 over p squared. And then you just take the product over all the primes. And then you have a box here. So if you use the inclusion exclusion or Mobius sieve, if you want to talk fancy about it, the idea is you get this, okay, over all primes, and then you just get x over zeta of q. So that's the asymptotic there. Let's see again how things match up. So if you're here with square free polynomials in FQT, is what you should get as a count is q to the n minus q to the n minus 1. Okay, and now you're going to say, well, dude, how do they match up? Like, you look at it, they don't kind of look the same. So let me make them look the same. So this is q to the n times 1 minus 1 over q. Okay, this is your x. And this is going to be your zeta of the affine line. So this is zeta of the affine line at 2. Okay, so let me just write the formula for the zeta function here. Well, you just count points on the affine line. So you're just going to get 1 over 1 minus q to the 1 minus s. And so if you plug in 2, you get 1 over q to the minus 1, and you get exactly 1 minus 1 over q. Okay. So this is, again, how they match up. And let me show you what you can actually do with the computation side of the geometry. Okay, so this is getting started to what I want to get at. So the idea is, okay, you have square free polynomials, and you want to count them in a different way, okay? So for now, I haven't used, again, what I use here is the zeta function. But what I haven't used instinctively is that when I say a polynomial, you should say I have roots, okay? So the idea is look at the roots, okay? So the idea is to look at the roots. And that's how we're going to cook up also our variety for what we want to do. So the idea is, so let me just write it here. The idea is to look at the roots and say what's happening, okay? So if you look at the roots of that polynomial, which is square free, and I should say also Mn. So if I forget to say this, always picture in your mind that I'm talking about Mn. So square free monic in Mn. Okay, if I look at the roots, I have Zi not equal to Zj. Okay? And then the idea is that if I say just this, then I won't determine the polynomial because I can swap the roots around, right? So the idea is I would mod out by the Sn action, which is free in this case because you don't have any fixed points, okay? So this would correspond to this, okay? And now we call this, so the idea is we call this the configuration space. So this is the configuration space. Okay, and now the idea is you can either talk over FQ, but I'll just do it over C. Because what I told you on that side is I can work over C. In most of the cases, I can move to C. And in this case, these are called hyperplane arrangements. So when you have hyperplane arrangements, you can actually pass to C because everything can be computed in terms of the lattice of the intersections. So there's a general theorem in topology which tells you like, okay, if I give you a hyperplane arrangement, you just have to draw what is called the lattice of intersection, and you can use that to compute your cohomology out. And if you have that, it doesn't care about what ground field you have. Characteristic doesn't put any play any role. Okay? So we have this, and now the idea is, okay, if we look at that formula, I'm gonna cheat a bit because I told you only for these kind of situations here. But the idea is you can use the same idea, is just work with quasi-projective things and then use compactly supported cohomology to get around those details. So basically, if I pass to C, I just have to understand basically, so understand two things if I want to count these. So one of these things is basically the action of Frobenius on cohomology. And the other thing I want to understand is what are the Betti numbers. Okay, and I can piece everything back in the formula basically. If I understand these two things, I can piece everything out. Okay, now this result here about the action of Frobenius on the cohomology if you have. So the idea is only works for hyperplane arrangements. This goes back to Lehrer, and this is.
How do we do like hyperplane arrangement? When I saw this, I really just in the Cn and take the points.
So you take here, sorry, so you take all the points Z1, Zn, and you remove all these Zi equals to Zj. Okay, so you take, basically this is C to the n, and you remove these Zi equal to Zj. You cut them out, and then you model by the Sn action. Okay. So as I said, the action of the Frobenius on the cohomology of these things, the tau cohomology of these things, is given by Lehrer in a special situation when you have a characteristic 0, and over a general ground field is due to Kim. And I told you there that the weights are at most that, and here you actually get for free, so the weights are exactly q to the I over 2.
And can you say, what was it that was over, what was in characteristic 0 in the first results you had?
So I think, sorry, this one was for a general, so the idea is this one with the tau cohomology can work over any field, but the idea is this one was proven initially, I think, for a ground field of characteristic 0.
But what does it mean to understand the action of Frobenius on cohomology? Or are you talking about the what are the Betty numbers question? Or
So I'm talking about the tau cohomology here on this side.
Okay.
So what the action of the Frobenius is on this guy.
Yes.
So I'm talking about this one.
Okay, so you are talking about the action of Frobenius.
Yeah.
So what are you saying that first result is about? It's about.
So the idea is how Frobenius acts on these like hyperplane arrangements. So on the tau cohomology of these hyperplane arrangements, and and in full generality it was proven by Kim that you actually get q to the I over 2. So if you act on HI, you get exactly q to the I over 2.
But what do you mean by the action of Frobenius, Q Frobenius, when you're in a field of characteristic 0?
That's
So I think Melody's asking about what Lehrer proved. If he was working in a field of characteristic 0, he couldn't have been.
Yeah, so the idea is,
So what did he prove?
no, the idea is, so I think he was working on purely like something like, so I think he was working on something like FQ. Yeah, I didn't read that part carefully about exactly the history of. Off the top of my head, I can't remember exactly that detail.
Okay.
So the idea is, but the most general thing, I mean, is due to Kim. Yeah. So now we got this piece out of the way, and the point is, once we get this piece out of the way, the kind of like only thing you're left to deal with is actually computing Betty numbers out. Okay. So, and Betty numbers actually were computed for this example by Arnold in '63. So Arnold showed that the HI of configuration space, and it doesn't matter which coefficient you pick, so I'll put just Q here. This one will be, so let me assume n is big or equal to 2. This will be 0 if I is big or equal to 2, and it's Q if I equals to 1, and Q if I equals to 0.
So let's stop and compute something a little bit here, Vlad, because something on the board is like not quite. We're gonna fix it, but here's my question. Let's talk about conf2 for instance.
Yeah.
Okay. So 2 points in the complex planes which are not allowed to be equal to another. So okay, and it's greater than equal to 2. So Arnold tells you what the cohomology of that space is. Yeah. So what Betty numbers does it have?
Okay. So this is Zi not equal to Z1 is not equal to Z2, and this is Z1 Z2. So this, if you use your topology 750, the idea is this one is isomorphic to the S1, to the unit circle, because you can just map Z1 Z2. You can do Z1 minus Z2 over the absolute value of Z1 minus Z2. So you can contract it down to that. So
So what cohomology groups does it have? Like which ones are not?
So the idea is this will have H1, which is, so the idea is there's an H1, which is isomorphic to Z, and
I think we're doing rational.
yeah, so this is Q.
Right.
And it will have, yeah, it will have also, yeah, the H0 is 1, because it's,
Yeah, H0 too. Okay. Now let's talk about how Frobenius acts on those and plug it into Grothendieck buckets. I want to see that. I want everybody.
yeah, so actually what you're right, because I'm kind of blind, because as I said, I'm using compactly supported cohomology, so that's dual to the usual cohomology. So the idea is it shifts the grading around. So basically, when you plug it in here, the idea is these, basically when you use the Poincaré duality thing, so this will change, so this H2 is Q, this will change back to exactly 0 and 1,
Can you
which
put
I
a
get
little
by.
C on that one? So we don't get confused.
So,
Oh, on the H2.
oh,
Or,
yeah.
what do you know, yeah. Oh, I meant for compactly
No
supported.
middle
Yeah.
seat. No middle seat.
Yeah.
Okay,
Okay.
okay, yeah, great.
But according to you, what are the weights? What's the action of Frobenius doing on those spaces? Because you've made a statement about how Frobenius acts, which is
Yeah.
almost right, but not quite.
So the idea is what I said here is in the projective setting, which is not what I have. So the idea is here when I said this is in the projective setting. So basically there I'm working the affine setting. So I should shift back these to Q to the I basically. If I do
Yeah, that should be a Q to the exactly.
Yeah.
Because there's no root Q in the number of
Yeah,
points
exactly.
in this thing.
Yeah. So the idea is, sorry about the confusion. So you have to really be careful when you're talking about affine. And so when I said the Q to the I over 2, again, here I wasn't lying because I was talking about the projective stuff. But here, I'm talking about affine stuff. So here, I'm a complement in an affine space. So that's why there is R Q to the I. Okay. So just, sorry about the confusion. Okay. So this is kind of a taste of what kind of is happening when you want to prove geometrically things. And now the idea is you can push this further. So the point is, if you want to cook up some statistics on this side in FQ of t, which is square-free polynomials, what you end up doing with that statistic is, okay, I'll just consider the same space as comp n of C, and then I'll just cook up something that encodes my statistic. So I'll just think about something, and the word for this is be like a sheaf, okay? So I want a system of coefficients, something that gives me what I want, okay? So the idea is, that's kind of the punchline in Jordan's paper with Church and Farr. That's the punchline, basically. You can encode any statistic you want, as long as you have a class function there, and you can cook up a sheaf that encodes everything out, and you just let this sheaf act on conf n, and you change the Grothendieck-Lefschetz to basically put here the sheaf coefficients, and you can change basically, once you have the sheaf coefficients, the idea is that gives you a representation. So the idea is you basically look at the representation. The representation is given basically by what you're doing to the Frobenius, basically. That's how you get the representation out. So basically, all you end up on this side is just computing some inner products out. So the idea is you'll get, so for any kind of statistic, okay, basically take a class function on Sn. So when I say take a class function, what I'm secretly using that every square-free polynomial has a decomposition. So here is, let me just explain this one. So every square-free poly has a decomposition into irreducible. And the Frobenius action on this will give you cycle structure, okay? So that's how you can cook up basically class function out of this. And what I'm saying is you get a formula which looks very similar to this, except you have a hyperplane arrangement, so the weights are like that, so everything is fine with the weights. And what you end up computing is, again, just the pairing of the singular cohomology with this class function, basically. So you just compute some inner products which are representation theoretic. So the difficult part when I say representation theoretic is actually understanding in that situation there we got away cheaply with it because we knew the quotient space, what cohomology it has, But here we can't get away cheaply. So the idea is you have to understand whatever you're doing here, you have to understand as a representation of the group you're doing. So the idea is to actually make it work, you have to do a bit more than what I said here. You have to understand actually the homology as a representation. So let me tell you about my problem and what you can do with the same kind of machinery. So the starting point is the following problem, which is namely, we have x, we want to see how many integers can be written as a sum of 2 squares. So how many? From 1 to x. Okay? So the classical result over z of Landau, so Landau basically prove that this is x over root log x times some constant k. Okay, so that's over z. So that's the main term. Okay, and this problem also was posed over function field. So this problem was also posed over function fields and solved. So these by Barry, Lior, Soraker, Yotam Shrilansky, and Adval Wolf. So solved, let me just say it with the caution word. Okay, so let me write what they proved. So let me just So when I say the function field version of it, what you should have in mind is, okay, look at a squared plus tb squared, and so which pole is in Mn can be written like this. Okay? So why am I doing this and not, so the idea is you'd say, let's do a squared plus b squared. Well, the point is, this guy, okay, so let me just say it here, if you're doing the right number to this is q of I over q, that's the extension there. So the idea is you want this to be also an analogy to that. So this comes from the extension fq of square root of minus t over fq of square root of t. And this is truly quadratic. If you are doing a squared plus b squared, you're doing an extension of the field of constants. You're doing fq squared over fq, so that's why. And actually that one was solved earlier on in 74 or 75, I don't know exactly the paper. That one was solved. So the idea is if you want to match up this statistic which you have here on this side, you better use this kind of one. Now the idea is that you get two types of results. Okay, so the first result is, okay, so let me write the analytic result. So their theorem 1, this is, and so the idea is let's call this number BQN. Okay, so this is the number of polys in Mn such that they can be written like this. So BQN is k of q over square root of pi q to the n over square root of n plus OQ of q to the n over n to the 3 halves as n goes to infinity. Okay. And I'll make some comments a bit about this part. Okay, and theorem 2.
Your real pi or just your?
This is, yeah, the real pi. Okay, so there's no like weird something else pi. Okay, and the second theorem that they had is BQN equals to 1 over 4 to the n, qn choose n, q to the n plus 1 to 4 to the n minus 1, qn minus 1, n minus 1, plus 1 over 4 to the n minus 1, 2n minus 2, n minus q, q to the n minus 1 plus O of q to the n minus 2. Okay, so let me make a bit of a.
And so, what did you ask? What's growing in that second case?
So the idea is this, so this is q to the infinity. and this is an ON. Let me just write it here. So the idea is, why am I writing OQ and ON here? The idea is, this error term here couldn't be controlled, depends on Q. And this error term here depends on N. So actually, Ophir Goradotsky remove the dependency here on Q. So you get the result without. So basically, if you remove this Q here, so you get a strong result in Q to the n goes to infinity, basically, if you don't have a dependency here, which is like an uniformity result over number fields. Okay, so that's kind of the status of it. What I actually worked in my thesis was actually getting this in a different way. So getting this and more out of it. So basically, let me tell you what I get. Okay, so and I would call this again. I would call this the analytic side. So the idea is how you get this is exactly the same kind of computations we had over Z, which using the analytic function out and computing some residues out. The way you do this is just some, so the initial proof is some complicated expansion out using some weird like sampling formula from like biology and so on. So the point is there's no natural explanation initially for where these terms pop up. So there's not, there wasn't a good explanation for this. So let me write what I do. So theorem, and let me explain a bit how it would go. So we can write BQN as sum of BKN Q to the n minus k, such that BKN is equal to sum of delta k j n 2n minus j for to the n minus j from j equals k to 2k. Okay, that's the first part. So basically, all your terms actually, even after this term here, all look the same. Like they have these binomial coefficients out, and then there are some numbers here. Now let me tell you a bit about these numbers. So delta k j n is equal to delta k j n plus 1. This is for n bigger or equal to 2k, and their size is bounded. So the idea is this size, I can actually control it. This is just 1.1 to the k. Okay. And actually, so I didn't write the formula down, but the point is, as you probably, if you want to go through my proof, you'll find actually a recipe where you can actually cook up all of these coefficients out. You can compute them as long as you want, and you can match them up, with whatever you have here. Okay, so the idea is, secretly, there's a recipe for computing them. Unfortunately, the formula is randomly write down, and I have no compact way to write it down. So the idea is that's why I don't write it. I just, for my purposes, I just bound it. And that's what I would get. Okay? So now, kind of, what's about the proof? Okay, so the proof will go in a similar style of looking at the roots. So if you're here, you look at how your polynomial splits. Okay, so the idea is the way the proof goes is okay. So take polynomial. So again, I'll prove it for square free again, and also without 0 as a root. So the idea is I'm using this space because there's a homology result over C. That allows me to do it for square free and without a root, and then I can bootstrap this result to actually get it for everything, okay? So the idea is the 0 you can put it in easily, because you just multiply, if you don't have a 0, you just multiply that side by a t, and you get the norm again. And if you're not square free, then if you multiply again that norm with a square, you still get the norm, okay? So you can just prove it here, and just bootstrap the result to the whole setting, okay? So, with this in mind, if you look at the roots, so the roots of your polynomial are now z1 to zn. Okay? And the idea is if I look at that extension fq So now I'll change the extension, because over function fields, it doesn't matter which quadratic extension you get, the count will be the same. So the A's, I'm using this extension here. So what I need to pick, basically, so what I'll pick is alpha 1 to alpha n, such that alpha I squared equals to zi. So I just make a choice. I didn't pretend. So there is, I'm not saying I pick them uniquely, just make a choice for each of these. Just make a choice of a square. Okay?
Sorry, I'm
Yeah.
very confused. When you say take a polynomial, do you mean there's a polynomial a squared plus tb squared?
Yeah, exactly. So the A's, I'm talking about this, how we prove it. So you take a polynomial which looks like, so if I'm changing the norm, I'm taking this norm, okay?
Wait, so you're saying you actually can deal with the polynomial with multivariables, not just two variables?
No, these are fq of t, and this is fq of t. So this is a polynomial still in the same ring. So the A's, this is, again, so the A's a, b are in fqt. So this is still a polynomial in fqt. And I'm asking which degree n monic can be written like a squared minus tb squared.
Right, then what are the 1, 2, 3, and...
Okay, I take a polynomial that can be written. So this is f.
Oh,
F has roots, these guys.
Oh, okay, sorry.
Okay, no problem.
Yes.
So f has roots, these guys. And what I'm saying is, the condition that you actually can write it down like this is, okay, so if you use the Gala theory side, let me just physically say what happens here, is if you make this a square, so if you do f of, okay, if you look over this guy, this f will be written as g of square root of t times g of square root minus square root of t. Okay, so I can basically, if you're a norm, if you just pretend you're over fq of square root of t, this is a minus square root of t times b times a plus square root of t times b. Okay, so that's why you can do this. So basically, it leads me to the idea, this is the same as saying, okay, so I can also say, the way I wanted to say it is, okay, I do f of t squared, and this can be written as g of t times g of minus t. Okay, so that's why I can take square root out the roots, okay? So the thing I've written is the same as saying, okay, plug in t squared for my polynomial, and then it should split as g of t times g of minus t, algebraic. So if I look at the square roots of these roots here, this will amount to alpha I squared not equal to zi. This two guys have to be co-primes. These have to be co-primes. So this is the easy Gala exercise that shows you, again, if you're a norm in this extension, you should factor out as this, where these two guys are co-prime in Mn. Okay? So this tells you that if you pick these guys out, you better not have trouble. Like you shouldn't have that, because you're square free, these guys shouldn't be like alpha a is not equal to plus or minus alpha j when you square it. Because zi, so here, again, this guy zi is not equal to zj. So if you square, the minus will give you the same here, okay? And also, I'm saying without the zero, so I'm saying also alpha is not equal to 0. Okay? And now the idea is the Frobenius action, because I have this condition here to be co-prime, the Frob action, okay? If I think, so now I have to be a bit careful, so let me not say something, it's okay? So now I think about, you have alpha 1 squared equals to z1. The idea is, there's also its sibling, which is minus alpha 1. So now the Frobenius, actually, if you take these two guys in pair, the Frobenius will move around these pairs, if you think about acting on the roots of G, basically. And now the idea is, once you go around a pair, you should end up in the same plus sign as you started. So the idea is, if you go from alpha I, this will pick up some minuses signs if you go around with the Frobenius acting on the roots, okay? So Frobenius action will give actually a sign permutation. So Frobenius is acting on these guys, z1 to zn, and this will act on the squares. So there is, you're moving this set into the next set, like alpha 2 minus alpha 2, but you don't know if you're taking the minus or the plus sign. You're blind to that, basically. But once you go around the cycle, you should end up in the same place, because these have to be square prime. So there is with basically an even number of minuses on each cycle. And the group that I have here is called Gn, basically, the generalized permutation group, or this is called in other language the hyperoctahedral group. Okay? And basically, those binomials that I wrote there, the first term is actually, if I look at the Frobenius action, as I said, I have to have an even number of minuses on each cycle, and that will actually give you the count, okay? So, if you think about, so this ln, initially this is what notation I use for this guy, this is the allowable permutations, sign permutations are from. Okay, when you act on the roots, this actually size of ln over gn will actually give you that binomial coefficient over 4 to the n. Okay?
So can you say that again for that? I mean, just because I went a little fast when you're at the end of time, but I think it's
Yeah.
good to say, you interpret that number, 1 over 4n, 2n, choose n that they get,
Yeah.
in a combinatorial way. And can you just write down, like, again, sort of in one place, like,
Yeah, so this number here,
yeah.
if you talk about geometry, is the allowable size of the allowable Frobenius action over the group, and it's also, if you think about gn, so this is sign permutations, which means plus or minus. So this has size 2 to the n over n factorial. So this is the mod 2z to the n times Sn, so this is size 2 to the n times n factorial. And this is the, so if you multiply by this guy here, you end up with the number of permutations which have an even number of minuses on each cycle. So again, when I say cycle, because you have the Sn, there's an Sn decomposition, and now basically your cycles are decorated. Let me say one last word. You can actually generalize this game. So there's, I didn't get to talk to the chance about the other papers, but you can ask more generally about these guys. A to the d minus t times b to the d. Okay? So now you don't want to do degree 2 norm. This is a norm from a cycloatomic field. Like this is like f cubed square root of order t of over f cubed. Of course, so this is not quite a norm because I'm kind of lying because you get more terms in the norm. But the idea is that what I can actually do is get the norm and then use another paper that I have with Daniel. This is the same spirit. You can actually go down to these kind of things because you'll get, so the idea is to get this, write it as a norm, and you get that polynomial in the norm has to have a lot of vanishing coefficients. And that will give you now the right variety. And then you just intersect it with somehow a similar complement. And you just care about the top degree. So you can just prove something about that top thing. It's in progress, but it seems to work. I mean, philosophically, it should work the same and gives you something about these. And these are notoriously hard problems. Because, for example, you're asking things like, which things are sums of 2 cubes? And that's, we know what the expected number is, I think, but nobody has proven like things like that yet. So that's one direction you can go.
So what's the answer for that one?
So the answer for that one, so the idea is here, you have to modify the power. This guy here will get the binomial, which is shifted. So the idea is, so this guy I should write it, so the truly way I should write is minus 1 over 2 choose n. If I'm doing hopefully the algebra right. The other guy that I should get with the main term is minus 1 over d choose n. Yeah. Yeah.
But I'm just saying, in that case, you're totally not going to be able to describe later terms. Like
Yeah, exactly. The later terms are inaccessible
terms.
because the point is you'll get a very highly singular thing like I get in my work with Daniel. But it is at least you can control the top side, the top term there,
Yeah,
which is A0. Yeah.
that relates to my question about which part of our paper are you using?
So the idea is we have, so the idea is there's a polynomial with a lot of vanishing coefficients, which means you get the symmetric sums in the roots have to be 0. And that's very similar to our like variance of function in short intervals. Because there you get to match up some coefficients of polynomials, but pretend your polynomial on the other side is like 0. It's having 0 side. It's in the same spirit, it's not the same, but it's very much in the same like
I'm not
genre.
quoting your result, but it's using the same.
Oh, is this like the whole
Slicing
thing
the
where you have like this lemma that shows like independence, sort of algebraic independence of like coefficients on the roots from coefficients on the like leading? Or
Kind of like that.
Okay.
Yeah.
So for the sum to Q, say, what do you expect for the power in A and in 1?
So the idea is, okay, so if you use the naive predictions, is, okay, if you want 2 cubes, it's x1 over third, and x1 over third. So you should get the x to the 2 thirds, basically, roughly speaking, plus a log term, and the log term, I don't remember the power, but it is, there's also a log term here that you should divide by. It's log x squared, but I might be lying.
And that's the prediction.
So the prediction, so there's, I didn't read about this prediction, but there should be a prediction of, because the idea is, again,
You
so,
predicted a prediction?
no, but the idea is this is in the general, like, what I'm talking about, this is in general, basically Bottom-Manning conjectures, because these are integral points, basically, on like y to the d minus x to the d equals to z. That's an equation like that, and we actually have predictions for general, like varieties. What is the number of the integral points? Those are again conjectural. They're complicated terms to describe, but I don't understand that picture very well. But I'm just telling you that it's part of a bigger story of counting actually points. Because the next also you can say, okay, the other thing I can say is I counted basically a squared plus tb squared, but I can go to rational. So I get to a conic and count points on a certain conic. And do, because again, this question was counting integral solutions like x squared plus y squared, but you can ask about rational solutions, and then you get to a conic at the end, like, which has complicated coefficient. That could also be another direction to go after this. But that's probably hard. I mean, I talked about with Jordan, he told me like, it's interesting, but it's hard.
So basically, this is like special case in computer, 5 varieties of integral points per computer.
Yeah, exactly.
In the function field, you can use that.
Yeah, so in the function field case, we have this, for some of them, we have this block that we can describe things in terms of the roots, and you get to count something with a variety easier somehow. Yeah. Okay, so I think I'm over time already, but if you have questions, feel free to ask them.
Okay, everybody out. Oh wait, questions. Oh no, okay, we're over time. Okay, we have a question. Let's do one.
But I just want to make sure I understand it right. So what you did is basically you have a integral polynomial, this a squared plus tb squared, defined over function field, and now you put a box on the range and ask how much.
No,
is
I'm
that
asking just, if you're in a man, how many things can you write as a squared plus tb squared?
Right. So basically you put a box in the range and then ask how much of these things in the image.
Yeah, exactly.
That's awesome. You should do it for more polynomials.
That's what we just said he was doing it.
Yeah, so the idea is that.
That's awesome. Okay.
Okay.
Does it make sense to ask for analogs of other number theoretic theorems, like is every one of these polynomials, can you write it as a sum of 4 squares, for example?
So the same theorems you have over Z should work over function fields. This thing, like, there's actually a fun paper I talked about at an MS chapter about, this is called the Pythagoras number of a field. Is what is the last number of squares you need to write elements in your field as a sum of squares? And it's a big, like, for like polynomial rings, we don't know that. It's a really fun question if you want to play around with it. We don't know, like, for some stuff we know it, but for like, you know, for whatever Q, you know, over a finite field, sorry, you can just do 2 squares because there you just use the stupid principle. You have x squared, then, you know, minus x squared, just you can write things as
So you could ask even for some kind of analog of Waring's problem, I guess.
People do.
Yeah, so there's a lot of different things that you can do. And also, what I didn't say, because I'm not a good analytic number theorist, you can use circle methods over function fields also to get these kind of things. So whatever, because you know, I know you like the circle method, but you can use the same kind of techniques to go also over function fields. They work the same. I mean, most of the techniques we have over Z just bootstrap analytically to function fields. But you get stronger estimates because, again, you have the Riemann hypothesis that leverages you better to get results.
All right, if there aren't more questions, everybody who's not on the committee, leave.